So we've just spent a bunch of time taking the derivative, and what we're doing now is doing the antiderivative. And just like it sounds, the antiderivative is just the reverse of the derivative. So let's go and write them definitions here. So the definition, the antiderivative of f prime of x is the function whose derivative is f prime of x. There's also a symbol for this. This symbol right here, it's always paired with a dx or a dt or some variable. It means take the antiderivative. So let's give an example. Let's say we started off with a function f of x equals 2x cubed. Well, we know from working with derivatives that if we want to find f prime of x, we take the derivative of 2x cubed, and we know from our rules that we bring down the exponent, subtract 1 from the exponent, 6x squared. That's taking the derivative. Taking the antiderivative, we're starting with this and we're just going backwards. So let's say we know that the derivative of f of x is 6x squared. Now what we want to do is find f of x, that original function. So we do that by doing the antiderivative. Let's take the antiderivative of 6x squared dx. And this dx tells us our variable. And this right here tells us take the antiderivative. And so what this is saying is it's saying find the function whose derivative is 6x squared. Well, we just looked over here, we knew what that was. It was 2x cubed. And we're going to learn a whole bunch of rules for this, but the first thing that I want to point out to you is that there's going to always, with an antiderivative, be a little plus c at the end of anything that we do. Whenever we do this antiderivative, always have a plus c at the end, and I'll explain why in just a second. But this is just the basic idea. We're just going backwards. So I want to start off with a couple of frequently forgotten things, and then we are going to go into the rules and how to use them. So right here, 2 important. But frequently forgotten things. 1. If you have an antiderivative sign, there must be a dx, dy, dt, whatever the variable is, there's got to be something that looks like this at the end. Very frequent to forget. It's not such a big deal with the level of calculus that we work with in this class, but when you do multivariable calculus, it really matters what your variable is. Also, whenever you take an antiderivative, there is a plus c at the end. This is probably the most frequently forgotten thing. And let me show you why that is. So let's say we're taking the derivative of x squared minus 2. You know that one, it's just 2x. If I take the derivative of plain old x squared, that's also 2x. If I take the derivative of x squared plus 24, that's also 2x. Really, no matter what this number is, the derivative of a number is always 0. So anything that's x squared plus or minus a number, the derivative is going to be 2x. So when I'm going the other way, when I'm saying, okay, I want to find the function whose derivative is 2x. So I want to take the antiderivative of 2x, find the equation whose derivative is 2x. I've said that like 3 times, but I'm just going to have you write this down. Function, find the function whose derivative is 2x. This could equal this, because this has a derivative of 2x. Or it could equal x squared because this has a derivative of 2x. Or it could be x squared plus 24 because that has a derivative of 2x. So really the idea is that this plus c just means we don't know what this number is. Any number could be here, and the derivative of this function would still be 2x. If we graph these ones, we can actually see sort of why this is the case. So x squared minus 2 is just down here, x squared is just right there, x squared plus 24 would be up there. All of these, if I draw them accurately, whatever number I have for x, I'm going to have the same slope of the tangent line for all of these curves. We just move them up and down without changing the shape of the curve. And so what this plus c just means is it means that I can take this x squared, I can move it up and down, it still has the same derivative. So make sure that you always have that plus c. Okay, let's start in on the rules. So these all parallel the rules that we had for derivatives. So old rules are turning into new rules. And I'm going to put our derivative rules on one side. I'm going to put our antiderivative rules on the other side. So there are a couple that we should be familiar with. Okay, I'm going to put these rules under the heading of what you can work with separately. So, we knew that if we had the derivative of some constant number, times f of x, that was the same as just that constant number times the derivative of f of x. The same thing is going to be true for antiderivatives. The antiderivative of c times f of x, remember that dx is always there, is simply c times the derivative of f of x, the antiderivative of f of x dx. Same thing. Likewise, we said that the derivative of f of x plus g of x was the same as the derivative of f of x plus the derivative of g of x. Same thing for antiderivatives. The antiderivative of f of x plus g of x, dx is always there, is just the antiderivative of f of x, dx, plus the antiderivative g of x, dx. I think these are a lot more symbols than the concept really needs, but that's the formal statement of it. What it just means is it means that if we have two things that are added together, we take the derivative separately, we take the antiderivative separately. That's all it really means. Now what we're going to get into is if you're taking the antiderivative separately, how do you actually mess with it? So the first thing we had for derivatives was the power rule. And we said that the derivative of x to the n, we just brought down the exponent, subtracted 1 from the exponent. In this case I'm using the x form rather than the box form, just for simplicity's sake. We also saw these with our boxes when we were using the chain rule, but if we just have an x and nothing in the box, this is the same form of that rule. Now the antiderivative is sort of going in the opposite direction. The antiderivative of x to the n power, dx is always there. What we're going to do is we're going to take x and we're going to add 1 to the exponent, undoing the subtract 1 here. Then we're going to divide by, instead of multiplying by, this new exponent. There is going to be a plus c at the end, just like I said before. Now notice if we come back to our original problem here, that's what was happening. We added 1 to the exponent, got x cubed, divided by 3, and this 6 divided by 3 just became that 2 right there. So the reverse of what we did to take the derivative. So we are starting the things that you need to have index cards for. So you already have index cards for this kind of a thing. You need to have index cards or flashcards for these as well. So you don't have to have them for these ones up here, but starting right here, all of the ones that I list on this side here, you need to have flashcards for, you need to memorize. The power rule is the most basic one. We're going to come back and work with them at the end once we get all the rules down. But then there's a whole batch of trigonometric functions. So the basic idea, if you remember our circle, this was our derivatives. We were going this direction. The antiderivatives just go the other way. Instead of circling clockwise, they circle counterclockwise. Like so. So whereas over here we had that the derivative of the sine of x equals the cosine of x, here we have that the, that the antiderivative of cosine of x is sine of x plus c, and there's always a little dx right there next to that. First we went this way, now we're going that way. So what you're going to have a set of rules just telling us this. So we know the derivative of cosine of x was negative sine of x, derivative of negative sine of x was negative cosine of x, derivative of negative cosine of x was sine of x. Here, just going the other way. Derivative of negative sine of x dx is cosine x plus c. Gotta have the plus c, every single one of them. The antiderivative of negative cosine of x dx, it's going the other way, negative sine of x plus c. Antiderivative of sine of x dx, negative cosine of x plus c. You can probably guess where we're going from here. There are more trigonometric functions. We know that the derivative of the tangent of x is secant squared x. Derivative of the secant of x is secant x times tangent of x. Derivative of the cosecant of x is negative cosecant x cotangent x. And the derivative of the cotangent of x was negative cosecant squared x. Going the other way, the antiderivative of secant squared x is tangent of x plus c. The antiderivative of secant x tangent x is secant x plus c. The antiderivative of cosecant x cotangent x dx is cosecant x plus c. Negative right there. Notice the negatives showing up in a little bit of a different place here. We're starting off with a positive and then it makes it negative on the other side. So these two look slightly different, but it's the same idea. Negative shows up when you're dealing with the cofunctions. And final one for this set. The antiderivative of the cosecant squared of x dx is cotangent x plus c. It is incredibly easy when doing these to become mixed up between this one and this one. So make 100% sure that you have these flashcards and you're going back and forth, mixing them up, remembering which goes which way. So there's one more batch. We've got the logarithmic and exponential functions, and then we'll move into practice problems. So, logarithmic, these also need to be with your flashcards. There's one really easy one. We remember that the derivative of e to the x was just e to the x. So that makes the antiderivative really easy too. The antiderivative of e to the x is just e to the x. Remember that plus c. Now here are the ones that are most easily confused. So we had that the derivative of the natural log of x equals 1 over x. So what that means is that the antiderivative of 1 over x dx is the natural log of x plus c. However, associating great, I've got 1 over x and then I get natural log of x leads to one of the most common errors that we see, which is to think that the derivative of 1 over x gives us natural log of x, which is it does not. So I want to write out another one. This isn't a formal rule because it comes from the power rule, but that the derivative of 1 over x was negative 1 over x squared. I want you to have this in your flashcards. You might want to just think of this as a memorization thing rather than a power rule thing, just because this is so easily confused. I also have another one. This is not one that we actually use in AP Calculus, but I want you to have this memorized as a rule simply so that you don't make this mistake of thinking that the antiderivative of natural log of x is 1 over x, because it's the derivative of the natural log of x that's 1 over x. So the antiderivative of the natural log of x is actually x, natural log of x, minus x, plus c. Let me write this over more neatly so there's no confusion about it. Right there. If you have this correct or not, I don't really care. We're never actually going to use it, but I just want you to be really clear that the antiderivative of natural log of x is not 1 over x. That's the derivative. 2 more, then we're done. The derivative of a to the x is a to the x times the natural log of a. You've done that already. That means the antiderivative of a to the x dx is a to the x over the natural log of a plus c. There's one final one that was in your cards. Log base a of x equals 1 over x times the natural log of a. There is no real equivalent to that one that we use. It's not really going to get confused in anything, so I don't think it's important to give you a formula like this. It is not going to show up on the AP test. Okay, make your flashcards. Lots of flashcards. Memorize your flashcards. Fun, fun, fun. Or the dragon eats you. Rawr.